Hi everyone. In this video we're going to continue on with section 6.3, and specifically in this video we're going to talk about graphing exponential equations using transformations. Okay, and so in order to do that we're going to have to examine the functional form of our exponential equation and see how slight differences in the equation are going to affect what our graph is going to look like. Okay? And so I've got a general form of an equation that we'd work with here. Okay, so this is my sort of general form, or at least it's a form that illustrates a number of topics. When we're talking about graphing exponential equations with transformations, we're always going to have, some sort of base function. And that base function, I'll call f of x. The base function is always going to be the base raised to some power. Okay? And so it could be any number. Specifically, we need an x because it's a function, so it needs to be a function of some number. Something has to vary in there. And so in this example, and all of the examples that we do, the x is going to be in the exponent. Okay? It wouldn't be an exponential equation if there was like x in the base. Something like x squared is not an exponential function. Okay? The x has to be in the exponent. So anyway, we have this base function, a to the x, and as we've seen before, if a is greater than 1, then the function is going to look like this. Okay, and there are certain properties, like this point right here is going to be 0, 1, so on and so forth. Okay, that's the basic function. And then when we add different things, like we see in our different kind of function right here, that's going to change the behavior of our graph. And so I'm going to go through a list of them and point to where each of them matters. Okay, and so this is extremely important to write down this set of things. These set of things, okay? So, we'll first start out in front of the A, right here, okay? So, I'll call that in front of the base. In front of the base, okay, that is going to control controls how quickly the function increases or decreases. Okay, meaning if I had something like 2 times a to the x, okay, when originally I had a to the x, what would change is that the new point where it crosses the y-intercept, or the new y-intercept, would happen at 0, 2, and it would look something like that. Okay, meaning it would increase faster. Now, the other important part of in front of the base is the sign. Okay, so in my example up here I have a negative, and the sign controls flipping over the x-axis. Okay, so if it's positive, then it's going to stay, because if it's positive, then it's going to increase just like the original function or the base function would, because it has a positive number out in front. But if it's a negative, then it's going to look like, if I change to black, the new function is going to go down. It's going to be the image of the other one, meaning if I flipped the red over, it should land perfectly on the black, okay? But so you see what happens to the negative out in front, flips it over the x-axis. Okay, so there are two things that can happen out in front. Hopefully that made sense. Now, for the second part, we have the sign in front of x, this sign. It controls flipping over the y-axis. It controls flipping over the y. So if I have a negative out in front of the x in the exponent, then it's going to look, if I use purple, like that. So you see, if I flipped the red over the y-axis, then hopefully it would turn into the purple. Okay, so the sign out in front of the base A controls flipping over the x. The sign in front of the x in the exponent controls flipping over the y-axis. Okay, and so then we have x. The next thing we have to worry about is this part right here. Minus or plus b, minus or plus some number. Okay, and so I'm going to call this addition or subtraction in the exponent. Okay, and so I mean this x minus b. Okay, and so the number inside that I add or subtract to x in the exponent, it controls the horizontal shifting. So it controls a horizontal shift. Okay. So, as an example, x minus b in the exponent, okay, it says I want to shift the graph to the right b units. Okay, so instead of this red function, let me do some erasing here. Take away some of this green and purple. Okay. So the red function, right? That's my basic function. Here, 0 or 1. If I shift over b units, that's going to literally take this function and just move it over that way. B units. Okay, and so my new function, if it was minus 3, then it would look exactly the same, but over 3 units. Okay, meaning this point, if I moved over here, is at 3, 1 instead of 0, 1. Okay, but has the exact same shape, so on and so forth. Okay, so that's inside the x. X plus b, just for completeness, x plus b means shift left. B units. All right? Negative minus is to the right, plus is to the left. In my mind, that always never made sense to me when I was going through, and I still have to fight against it. I always think plus would be to the right and negative minus would be to the left for some reason in my mind, maybe because of the way we work with number lines. But, in fact, minus is to the right, plus is to the left. So make sure to keep that straight. Now, the last part that we have is this plus c. It's outside of the exponent. You're just adding or subtracting a number to the exponent term, okay, or the exponential term, meaning this whole a raised to some power nonsense, okay? That plus c controls vertical shifting, okay? Plus c is going to shift this graph up c units. Negative c or minus c is going to shift it down c units. Okay, so it controls the vertical shifting. And this example probably works more of the way that your mind thinks. Plus is up, minus is down. Okay, and so that's the basics of graphing an exponential equation using transformations. Now, let's get to an actual example. Okay, so what I want you to do, or what we're going to work through, is graphing the function 2 to the negative x minus 3, okay, and then determine the domain, range, and horizontal asymptote. Okay, and so graphing the function isn't going to be too bad because I have actually the graphs here so that we can look at it. The domain and range shouldn't be so challenging, but then this horizontal asymptote business we haven't really done before, so we have to take special care in doing that. Okay? But first, we want to graph the function, and that I've made easy here, okay? Because I've put the pictures of how you sort of transform this in steps so that we can see what's happening. Okay, so we start off in the leftmost picture. I guess I'll call this picture 1, I'll call this one picture 2, and this one picture 3. In picture 1, we start with a base function, 2 to the x power. Okay, so that's what 2 to the x power looks like. When I add in the negative up top, and I just look at the exponential term, in other words, I'm looking at 2 to the negative x, you'll see that the difference between picture 1 and picture 2 was that picture 2 is very similar to picture 1, but it's been flipped over the y-axis. Okay, and so I denoted the y-axis in picture 1 with the dotted lines. If you flick the picture over, then that's what you get. And what you mean, or what I mean by flipping the picture over, is if you look at the points, all that's happened is it's turned every x point on the graph that they've plotted to be negative. So originally I had 3, 8. Now I have negative 3, 8. I had 2, 4. Now I have negative 2, 4. 1, 2, negative 1, 2, 0, 1. Negative 0 is still 0, so 0, 1, it stays the same, so on and so forth. Okay, so that's all that it means. Literally, it means I put a negative in front of the x, which means the x values switch, or they become negative, and the graphical representation of what happens then is that the graph flips over the y-axis. Okay, so anyway, and then we add the third step, 2 to the negative x. We subtract 3, and what happens is that it moves down. It went down 3 units. Okay? So same exact pattern, but it just moved down on the y-axis 3 units. So instead of having the point or the y-axis be 0, 1, it's now 0, -2. I literally subtracted 3 from all of the y-coordinates. Okay, and so you can either think of it as the full graph or of the points, whichever works for you. Okay, so anyway, this is the final graph. Number 3 is the final graph of the function. And so now we need to determine its domain, range, and horizontal asymptote. Okay, and so domain is not too bad. Are there any numbers that I can substitute in and get an error or something weird out? The answer is no. And so the domain is from -infinity to infinity. Okay. Now comes the range. And if you look at graph number 3, the graph looks to be going down towards the line right here, y equals -3. And in fact, it'll get really, really close, and it'll almost touch it, but it'll actually never touch that line. It'll only get arbitrarily close. And so the range is -3 to infinity. Okay, it goes as low as -3 and then all the way up to infinity. And notice that I'm using parentheses and not brackets. That's because I never actually hit 3. I only get close to it. All right. And then the last one, the horizontal asymptote. Right? That's the line where the function gets really close to it but doesn't actually touch. That line is y equals -3. Okay, so that's my horizontal asymptote. And so that's how you graph an exponential equation with transformations. Okay? And so what I'll often ask from you when we actually do these types of problems is maybe not necessarily to graph it, because that's going to be hard, but to describe what happens in each situation. Okay? And so I would describe from graph 1 to graph 2, that would be a horizontal or a flip over the y-axis. Okay, so to get from step 1 to step 2, I flipped over the y-axis. Okay, and then in step 3, this -3 part here was a vertical shift of -3. Okay, so I flipped over the y-axis and then a vertical shift of -3. So if I asked you to explain in words, that would be what I expect. Okay, so now let's do a quick example, okay, and then of course you'll have a your turn. So what we have here is a graph of the function f of x is equal to 3 raised to the 2x plus 1. 3 raised to the 2x power plus 1. Okay? So if we thought about the original function, and I'm not going to necessarily require this of you, but I will roughly sketch each of these functions. Our base function that we're working with is, I'll call it maybe g. Our base function g of x that we're working with is 3 raised to the x power. Okay? And so 3 raised to the x power crosses the graph at 0, 1, and then the other point is 1, 3, and then -1, 1/3. Okay, and so it looks like that. Okay, I know it's a rough sketch, but that's what it looks like. That's 3 to the x. Now we take the second part, which is 3 raised to the 2x power. Now this is The only part that I didn't talk about last time, when I have a 2, when I have a number in front of the x, what that does is called a horizontal stretch. Okay, and so it literally stretches out the graph to be twice as slow in increasing or decreasing as it usually would be. Okay, and so to see the effects of that, it would still cross the y-axis at 0, 1. Okay, but instead of being at 1, 3, would be that next point, it would happen at 2, 3. Because I multiplied the x by 2. Okay, so it would happen at 2, 3, and then it would level off even more slowly. Okay, instead of negative 1, 1/3, it would be negative 2, 1/3. And so the graph is going to increase, although still increasing fairly quickly, it increases at half the rate. Okay, and so maybe my graph doesn't do it justice enough. It would be out here. Okay, and so hopefully you can see the distinction, although it's a very rough sketch, that a graph 2 here is increasing much slower than graph 1. So the way you would describe that second step when I multiply x by 2 is a horizontal stretch by 2. Okay, and then lastly I have plus 1. So 3 raised to the 2x power plus 1. What that does is that's a vertical shift of positive 1. It moves everything up by 1. And so instead of having the y-axis be 0, 1, it's now 0, 2. Instead of having this next point at 2, 3, it happens at 3, 3. Oh, sorry, it happens at 2, 4. Up here, instead of having negative 2, 1/3, it happens at negative 2, 1 1/3. Anyway, it moves up by 1. Okay, and so I have the same general shape, or at least it's supposed to be in that third graph. There is the second one, but it's just shifted up 1. Okay, and so it's important for the horizontal asymptote purposes in the range to remember that the horizontal asymptote of the base function was at y equals 0. Okay, so it got arbitrarily close to the x-axis, but it never touched it. So now, when we look at the domain, the range, and I'm just going to call it the horizontal asymptote, HA, you see that the domain, which is usually going to be true of all of these functions, it's from negative infinity to infinity. Okay. The range, it certainly goes up to infinity as x gets larger and larger, but as x gets more negative, this number is going to decrease until it almost hits 1. But it's never going to reach 1. So the range is 1 to infinity. And the horizontal asymptote, because we shifted up 1, goes from y equals 0 to y equals 1. Okay, and so all of these together constitute an answer. All right, so hopefully that made sense. Here's a your turn. Try it out. It's similar to the first example that I did. So you can look back and see what happens there. For this, I don't want you to graph. I want you to say what steps happen. Okay, and so from, say, 2x to negative 2 raised to the x power there, what happened in words? Okay. If you would like to graph the function, that's fine, but I'm not going to make you graph it. So what happens in words when I multiply by negative in front of the 2x, and then what happens when I have plus 5 there, say in words. Then determine the domain, range, and horizontal asymptote.